air cycle technology was formed to take existing knowledge of the thermodynamics of air cycle cooling and some of the hardware that's been used, say for example in the aerospace industry, and bring it to a compact, affordable application on internal combustion engines. Steve and I are old colleagues. We came together to form a company to take this thing to market. And the process has been to heavily using modelling to demonstrate the capability of the system to deliver the cold air, and to even with the modelling we have available, Amesim, to predict the improvements in combustion through the built-in combustion models. That was shown to a lot of people, and it was accepted that was viable and sensible. So we then moved into trying to develop some hardware. So we had basically the core element of the system is the hardware you can see here, a turbo expander. Combustion is surprisingly sensitive to just temperature, regardless of the pressures. So in gasoline engines you have a condition called detonation, where as the temperature goes up in the cylinder, there's uncontrolled combustion, and it's beginning to be the limitation of both power and economy of engines, as engines are more and more highly tuned, even in the OE market, never mind the performance market. That detonation control has become critical. So that we're offering a solution to that problem by reducing the charge air temperature. We can expand what they call the detonation margin, optimize the engine, improve the fuel economy. The modelling did a lot of the talking for us. We then moved on to building some demonstrator parts, which we put on a simple car originally, drove it around, measured everything, correlated back to the model, proved that it all worked fine. Then the difficult bit was to make the hardware work. So the turbo expander, originally it was very easy. We took an existing turbocharger, which used hot exhaust gas in the turbine. We use cold air in our turbine. We started with a turbocharger. We took off the hot turbine bits. We put on cold turbine parts, which we've designed. So we design everything you see on the cold side, as it were, of the turbocharger. That turned it into a turbo expander. But we carried on using the other parts from existing turbochargers, because the parts are easy to find and they're infinite variety of parts. And then the step after that is probably what you see here, where we deleted the oil cooling system of a turbocharger, because turbochargers run with engine oil lubrication circuit. They run very hot. That oil has to be passed through the engine quickly. We don't have hot anything hot, but we do have high speed. So we've switched to sealed ball bearings. That's a reasonable challenge. This device runs at about 100,000 RPM, so we're pushing towards the limits of sealed ceramic ball bearings. But we found some, and we've, again with the help of the bearing manufacturers, we've analysed them, and they are certainly fit for purpose. So what you see here is our cold air turbine design, our housing with the sealed bearings, but still using recognisable turbocharger parts for the compression side. So an OE compressor housing and an aftermarket compressor wheel. And then as of today, or a week ago, we're now sourcing more of our own parts. So the next stage is this compressor housing, which is more to our design, made for us, and visibly smaller and lighter, and therefore cheaper. So and the compressor wheel that goes with it will be our own design as well. And that's where we are today.
I've known Chris for something over 40 years. I knew how good an engineer Chris was, but I've been pretty impressed by what we've done, what we've achieved in a short space of time with, pretty limited resources. We don't have hundreds of people. We don't have millions of pounds worth of debt. We've just got on and done it, and that's mainly down to Chris and all the kit he's got in terms of the software that enables us to do so much so quickly, which has been brilliant. So yes, compared with a lot of other companies that we come across, startups or sort of mid-range, mid-term businesses, we're in a much better position, and we are a lot faster moving. And we've had small success commercially, but only on a limited scale so far. We don't actually employ anybody because we use contractors, and partners. We don't have an office other than what's in our residences. We have a workshop where we now have our test rig and an assembly line. So it's very much a low resource, sort of a high intelligence way of going about stuff. And it means we're very, very fast on our feet. So as a company, we're very small, but I think we punch well above our weight.
So we're very busy now tidying up some results of some demonstration testing we've been done on a high performance road car, which we're aiming at the low volume tuning market, and generating as much high quality data as possible to keep the OEs interested, or to, as ever, to keep supplying them with the extra bit of work they'd like us to do before they decide to commit, which is how they work. So we're in reasonably good shape. We're pretty happy with how it's going. We've got full suite of designs. We've got obviously 3D modelling. We've got our 1D modelling using Amesim has served us extremely well. That's taken us also into the control system. This is a core of a system which has some coolers, some control, flow control valves and so on. We've designed that control system, which is also being made for us by a low volume control system manufacturer, but to the OE standard DIN 26262 type standards. I'm not an expert in that. And we've used the 1D Amesim modelling also to predict the transient response of the system, and that's been validated with test data as well. So full modelling, predominantly 1D, but the combustion 3D model there when we need it. Obviously the full 3D design. We've built a test rig where we can drive this under control conditions. That measurement, we've also modelled the test rig, so we designed the test rig using Amesim, and that was absolutely spot on. So we're good to go now. On the turbine side, an exhaust turbine of a turbocharger is about 60% efficient. This one, a cold air turbine, is running 85% efficiency, measured and predicted. Also using Amesim. That is a very unique feature of Amesim. We can do a 1D design of a turbine and generate a 3D performance map. And it's we're very pleased with it. We can predict the performance in 1D within 2 or 3% of a full 3D CFD model of the turbine. So that's proved extremely useful for us. Obviously, it gives us an element of exclusivity as well, and IP around that. Yeah. So we're showing quite a significant evolution for the same flow and performance. We managed to come down from this modified aftermarket mainstream supply unit to our own low volume design, and we're saving on size, weight, whilst matching the performance of the original one. Yeah. This is all about credibility, isn't it? A lot of it, they get people knocking on the door all the time, so it's as much proving that we're capable people to do the work. That's almost as important as what the actual technology is. Our track record, our experience, how we go about our projects, simulation that they can both believe in and actually use in house, of course. And we can, for example, our turbine model, we can encrypt that, as you know, within Amesim, so we can give them a black box model and they can run turbine simulations then in-house. So that sort of ability to both share information and protect it as well is really useful. But yeah, it's recognised that we're working at the level they will work themselves if they're in-house.
Siemens, ingenuity for life.